Yeah, so I would like to give a short tutorial for projpred with first some introductory words. Projpred is an R package implementing the projection predictive variable selection that I abbreviated here by PPVS. And this is a special variable selection technique for Bayesian regression models, which are typically fitted by the rstanarm or brms R packages. But in general, it's not restricted to models based on STAN. Yeah, so the projection predictive variable selection, as I said, it's a special variable selection technique. And it's important that it also allows for valid post-selection inference. A key component of it is that it requires a reference model. This is the best possible model in terms of predictive performance that one can construct. So often this is the full model with some shrinkage prior, for example, the regularized horseshoe prior or the R2-D2 prior. But sometimes it can also make sense to use some dimension reduction for the predictors, for example, by principal components. And then the aim is to select the smallest submodel achieving the best predictive performance with respect to the reference model's posterior predictive distribution. And yeah, so that's kind of an overview. And now the projection part. The projection means to project the reference model's posterior onto the parameter space of a given submodel. This is done by minimizing the Kullback-Leibler divergence between the predictive distributions of these two models. Typically, the reference model's posterior is clustered or thinned, just for computational convenience. It's also important that this is a deterministic transformation, apart from clustering algorithms, which might be initialized randomly, for example, k-means. So a prior is only needed for the reference model. In general, the projection problem is not easy to solve because it involves an expectation over the reference model's predictive distribution, so posterior predictive distribution, possibly clustered or thinned. But yeah, this expectation makes things complicated. In some cases, and luckily these are the most common cases, at least for in terms of regression models, the projection is equivalent to fitting to the fit of the reference model. And this in turn makes things a lot easier. Yeah, so this was the idea. I've included 2 slides here for a brief history of the PPVS, but I think I'll have to skip them. Perhaps we have time later, or you can inspect them yourself if you want. I'd like to head over to the example. And for this, I'm using the body fat data from the th.data package. Yeah, the structure of the data set is shown down here. Dex fat is the response variable. All others are predictive variables. 71 observations. And I've already scaled the predictors here, which is needed for the R2-D2 prior as implemented in BRMS. I've also centered them, but this is not the important point for the R2-D2 prior. Yeah, so this is the data set we want to work with. And the first step is to fit the reference model. Here I'm using BRMS, and I'm using the full model and also including all two-way interactions. And yeah, an R2-D2 prior for the coefficients, for the regression coefficients. And the rest of all this is not that important. Then after fitting the reference model, we have to check the MCMC diagnostics. We usually want to inspect basic posterior quantities and also investigate predictive power. I've skipped all these steps here because they're not really specific to projpred, but rather to the reference model. Yeah, the last step is especially important because, as I said, the reference model is supposed to be the best possible model in terms of predictive performance that we can construct. So yeah, we want to make sure that the predictions make sense, at least in form of a posterior predictive check. Yeah, so now we're heading over to the projpred part. And here the main part is to run varcel or CV varcel. And yeah, these functions include two main steps. First, varcel. The first step is a heuristic search, either forward or L1, thereby fitting to the fit of the reference model, so performing some kind of projection. This gives us a so-called solution path, which is simply a character vector ranked by predictive relevance and containing the predictor terms. So the most predictive predictor term is first and the least one last. So yeah, this gives us the best submodel for each size. At this stage, this is still an internal object. We will come back to this later. Now, the second step is a performance evaluation. This means to calculate some predictive performance utility or loss along the solution path. So for each submodel along the solution path. And yeah, an example utility is expected log predictive density, ELPD, which is also the default utility. But in classification problems, for example, it can make sense to use accuracy. Yeah. So this was varcel. The internal procedure of CV varcel is basically the same as in varcel, but with a cross-validation. So either k-fold cross-validation or Pareto-smoothed importance sampling, leave one out cross-validation, which is an approximate leave one out cross-validation. And yeah, as you can imagine, CV varcel is recommended over varcel to avoid overfitting due to the cross-validation. But it's also important to mention that varcel offers the performance evaluation on independent holdout data. But yeah, in that case, we have a single holdout data set. Yeah, so here in our example, we'll use CV varcel with the default cross-validation method, pieces loop, and a forward search. First, yeah, it's important to know that CV varcel is quite costly in computational terms. So it makes sense to perform a preliminary run in order to restrict the maximum size up to which we want to run the search. So here we call CV varcel with a validate search set to false. So this means that the search is run only once with the full data set and not for each cross-validation fold separately. And if we plot the resulting object, we get a plot like this. We'll see a second plot, which is very similar to this one later, but the point here is that you can see that the performance utility levels off at least from size 6 on. So there's not much change anymore in predictive performance from size 6 on. So we can restrict the search in the next CV varcel call to submodel size 0 to 6, which is now done here. So we now run CV varcel again, but with the costly default of validate search true. So the search is run for each cross-validation fold separately, and n-terms max set to 6, meaning that we restrict the search to the first 6 slices. Yeah, this is the resulting plot, and now I want to go a bit into detail. So in the plot call, we have set deltas to true, which means that this is not really the ELPD on the y-axis, but the difference of the submodel ELPD compared to the reference model ELPD. So the reference model's performance is at 0, here the red dashed line, and the submodel performance then in black. The uncertainty bars are plus minus 1 standard error. These are derived from the cross-validation folds. Yeah, and now the point here is to see where the submodel predictive performance approaches the reference model's performance close enough while still achieving a submodel size which is as small as possible. And this would be size 3 here. We can say, even when we take the uncertainty into account, that size 3 should be sufficient. In real-world applications, it could make sense to also investigate size 4, whether this improvement is important. It also depends on the application-specific trade-offs of sparsity and predictive performance. But here we'll use size 3. So this is our manual decision based on the plot. We assign it to some object. Alternatively, there's also a function in projpred called suggest size, which gives a heuristic suggestion. Here, this would also give 3. And now we can retrieve the solution path using function solution terms. As we have restricted the search to size 6, these are only 6 terms. And these are sorted by predictive relevance. So hipcirc is the most predictive one. And now we can restrict this solution path to the selected size. We use the first 3 ones, so hipcirc, anthrophore, and wastecirc. These are the predictor terms for our final model. And now for post-selection inference, as I said, a key property of projpred, or the projection predictive variable selection, is valid post-selection inference. And for this, we project the reference model once again onto the selected submodel using function project. And this gives us an object that we can call s.matrix upon. And this gives us the matrix of the projected posterior draws. This matrix can be used like any other matrix of MCMC draws, but in case of clustered projection, we need to take the cluster weights into account. Here, this is not clustered, so we don't need to take them into account. And we also need to be cautious with respect to the interpretation of these projected posterior draws, because in general, projected regression coefficients do not reflect isolated predictor effects. Yeah. Now that we have obtained our final projected posterior, we can inspect, for example, the marginals of this projected posterior using the posterior package. Yeah, this here I've calculated the median, the MAD, and tail quantiles for each parameter. And the output is shown down here. This is very similar to the summary output given by brms or rstanarm for posteriors, not projected posteriors. Yeah, so as you see, the handling is like other MCMC draws. We can also plot the marginal posterior, the marginals of the projected posterior using the base plot package, for example. Yeah, in a real world application, it wouldn't make sense to include the intercept here because it is on a different scale, but for illustrative purposes, I've included it here. And apart from the marginals, we can also make predictions based on the projected posterior. There are two options for this. The first one is projpred, which is similar to posterior linpred, for example, in rstanarm and brms and so on. And this calculates linear predictors, possibly transformed by the inverse link function. And it also has an argument called integrated, which when set to true, will calculate the average linear predictors across the projected draws. Then the second option is projpredict, which is similar in spirit to posterior predict. This gives us draws from the posterior projection predictive distributions. And so it also encompasses the uncertainty from parameter estimation, like projlinpred, but also from the observation model. And this is useful, for example, for posterior projection predictive checks. I've termed them PPPC here. And yeah, now I want to illustrate these two functions in turn. First, projlinpred. For this, we assume to have a new data set as shown here. Yeah, the details are not that important, and I've also realized that there's a bug in projpred, or at least at the intersection with brms. But yeah, we have a new data set with 3 observations here for the 3 selected predictors, and we want to calculate the expected values of the posterior projection predictive distributions for these new observations. So we use projlinpred for this, pass the new data set to argument new data, and we set integrated to true. Yeah, this works here for the Gaussian case where we have the identity link. In other cases, we would need to transform true. Yeah, so we get a single value for each new observation, and we can append it to the new dataset as shown here. And projpredict, as I said, is useful for PPPCs, here visualized with base plot. So we don't need to use argument new data here because we're doing in-sample predictions, and we can visualize them with PPC dense overlay, for example. And yeah, you can see here that the predictions generated by the model in light blue are in general similar to the observed response values, the corresponding kernel density estimate in dark blue. Well, up here there are some deviations, but in general, this is okay. Yeah, so this was the example. The original computing environment information, I've sent it to the organizers. in case you want to reproduce results. And now a last slide concerning the supported models. In terms of the response, the current CRAN and GitHub versions are limited to the Gaussian, binomial, and Poisson families. But extensions for more families are soon to be included, the latent prediction and the augmented data prediction. And on the side of the predictors, as shown in the example here, conventional population level terms are possible, but also multi-level, so group level terms, and additive or smooth terms. And for further information, you can take a look at this section of the projpred vignette.